Oh, whether slides are visible?
Yes, sir, visible.
Yes, sir, visible, visible.
Yeah, yeah. Actually, now I cannot see from my side. So the title of this talk is the energy storage beyond battery and capacitor. That is your supercapacitor. So outline of the presentation is like this one. That is, first part is the basic requirements. Second one is the experimental work. Third is the theoretical work. So see that it is very important to have this theoretical work also. So part of that work that has been covered by Professor M. Lakshmanan, and I should acknowledge him that with his guidance that we could extend the fractal analysis in the thin film. So let us see this basic requirement for the energy, and before that one can see that nowadays there are 3 E's which are primary issue and concern of human development. So these E's stands for energy, environment, and economy. In general, the clean energy, or one may say that the environmental friendly energy, can be divided into 3 parts. It's harvesting from renewable energy sources, conversion, and storage. Among all the 3 parts, energy storage is an essential part, as it is directly linked with the day-to-day life of human beings.
Excuse me, sir.
Yes, please.
Sir, your slides are not changing.
Pardon?
Sir, your slides are not changing.
Okay, okay, okay. So maybe just a minute. Yeah. Oh. Yeah, I will take care. I will take care later on. So we're talking about these 3 E's, and in India, it is the fastest developing economy in the world. So a huge amount of energy resources are needed to fulfill the needs of 136 crore population. According to the Ministry of Renewable Energy, India is targeting to increase its electricity generation up to 350 gigawatt, whereas the electricity consumption in India is extrapolated to increase up by 400%. So this poses a great deal of thinking in direction of synchronizing the need and supply. So it is very important to see that energy is being produced. So we have to, first of all, that we have to increase the production. So after increasing the production, the next thing is the storage, because as and when you are going to produce the energy, that energy may not be used at the same time. But here we think that how can we store it? Once we have stored the energy, then that can be used later on and at the same time also. So now come to the basic requirements here, that how we can come to the supercapacitor related things. So for that, I would like to introduce here that nano. So what is nano? Because we all are talking about the nanotechnology. So we should know that what is this nano. So this word nano comes from the Greek word nanos, which means that is very small. So very small, but at a scale, if you see that meter scale, 1 billionth of the meter, that we call as the nano. So one can compare here the different things with this nano at nano scale. That human hair, it is approximately 80,000 to 1 lakh nanometers wide. Human DNA, that is 2.5 nanometers in diameter, and this inch that has been here given, that number nanometers in this inch. Similarly, one can see that a sheet of nano papers is about newspaper, it is about this one 1 lakh nanometer thick one, and marbles and gold atoms that one can see. So once we are going to nano scale or making this nanomaterials, then it is having the many applications. So it is having the applications in physics, chemistry, engineering, biology, and so on. So nanomaterials are going to be very important one. So one can see that why the property of the nanostructures are different from their bulk materials. Same thing is there, that if you are going to the nano scale, then what changes are occurring there. So scientifically we have to see that what is going on there. So two principal factors are responsible to unique physical and chemical properties of the nanostructured material, which are different significantly from their bulk materials. So same material is there. If it is in bulk, then it is having the different characteristic, and if you come to nano scale, then it is having the different characteristic. So what are those? There are two factors. Number first one is quantum confinement effect, and number second, increase in a surface area to volume ratio. So these two important factors, they are responsible for the changes if you are going to the nano scale. So what is this quantum confinement scale? That when size of a nanocrystal is smaller than de Broglie wavelength, that we all are familiar with the de Broglie wavelength, lambda is equal to h upon p. So that was given by Professor de Broglie, and it is interesting to state here that Professor de Broglie, basically he was the student of history, and then he has started learning physics, and in his PhD thesis he has proposed this idea that a moving particle will behave as a wave in 1924. Yeah, 1924. And in 1927, Heisenberg, they developed the the Schrödinger. The Schrödinger developed the Schrödinger wave equation, uh, uh, and then in 1927, the G.P. Thomson in England and Davison and Germer in UK independently, they have proved the existence of the de Broglie wave. And in 1929, just after the 5 years, de Broglie got the Nobel Prize of the Physics. So a student has developed this concept and he got the Nobel Prize of the Physics. See that how revolution that has come. So here I should state that we should observe the happenings in the nature and then try to explain it by some way or the other, and chances may be that we are the first one who is thinking in that direction. So many discoveries that has been taken place. Similarly, the Berry phase. So I met Professor Berry. He told that when I discovered this phase, then I thought that it is going to be the very general one, and I was searching so many quantum mechanics book, and he was telling in this way that I was sure that I'm quoting it that it will be there in quantum mechanics book, but I could not find it. Then discussed with my friends and found that it is a unique one. So that is again discovery. So please try to observe the happenings in the nature, and once again I am repeating that chances may be that you are the first one who is thinking in that particular direction. Now come to this quantum confinement effect. So first point is here that when size of nanocrystal is smaller than de Broglie wavelength, electrons and holes are especially confined and electric dipoles are formed. So there, since they are confined one, then electric dipoles that will be formed and the energy levels become discrete. So due to this the formation of these dipoles, what will happen that energy levels are becoming discrete one. Similar to a particle in a box, energy separation between two adjacent levels that is increases with decreasing the dimension. So as you are decreasing the dimension, then one can see that there is a change in the energy levels. The unique optical and electrical properties of nanomaterials arise due to quantum confinement effect. So one can see it here that optical and electrical properties are being changed. So now come to the second part here, that is increase in surface area to volume ratio. So what is happening? How the surface is being increased. So I have taken here example that one box here, and the dimension I have taken 1, then total surface area, that height multiplied by width multiplied by number of sides multiplied by number of boxes, so it is going to be 6, and total volume if you calculate, then it is coming as 1. Then surface to volume ratio, so area upon volume, it is going to be 6:1. Now I have increased it 5 times. This cube that has been increased here 5 times. Then total surface area that has been increased here 150. Total volume that is also increasing 125. But see here, surface to volume ratio, it is going to be 1.2. But here, if you are taking a bulk and divide into here different cubes of the dimension of 1 unit here, then one can the total surface area, it is becoming 750. Total volume that is remaining the same as 150. So surface to volume ratio, it is increasing, it is going to be 6:1. So same material is here, same object is here, but if you divide, then this surface area, it is going to increase. So there are these two important points are here, that is quantum confinement effect and increase in surface area to volume ratio. So one can see it here, that is density of energy levels, and here it is the energy. So this band gap, one can see here that when it is your bulk, then band gap we are here having like this one. When we are going to thin film or the nano, then it is energy levels are changing here. In nanowires, the energy that is being changed here, and nanocrystals, one can see that energy levels, that is discrete energy levels that we are getting. So the electronic configurations of the nanomaterials are significantly different from that of their counterparts. So due to this one, there will be a change in the optical and electrical properties. So these properties are going to be size dependent. So what is this electrical conductivity? The effect of size on electrical conductivity of nanostructures and nanomaterials are complex. See that it is very easy to say that if you are doing like this one, then it is changing. But if you deeply try to understand it, then nature is going to be a very complex one. Since they are based on the distinct mechanism, there are the many mechanisms. So these mechanisms can generally grouped up into 4 categories. So there are these 4, that is surface scattering, including grain boundary scattering, quantized conduction, including ballistic conduction, Coulomb charging and tunneling, widening and discrete of the band gap, change of microstructures. This is going to be the new field here, or a field where one can work and try to find out what is going on there. So we have seen that nanomaterials. Now come to the thin films. So as I have developed the thin films, so it is better to introduce the thin film. So a thin film, it is a thin layer of material over another material. Commonly we call this one as substrate, ranging from fractions of nanometer to several micrometers in thickness. So on the scale level, one can see that this is the thin film. So a lot of researches are going on thin film. At the same time, it is important to mention here that researches are also going on thick film, because here also some important characteristics are coming there. So one can see that this is the substrate. So substrate has been taken, and above this substrate, a thin film that has been synthesized. So thin films are of 4 types. So first one is the single crystal, epitaxial, polycrystalline, and amorphous. So these are the types of the thin films. So one can now come back again that if we compared with the bulk material, then Physical properties of the particulate deposits and thin films on substrates may strongly differ depending especially on the development of structure and morphology. See that when you are depositing a thin film, then its structure, that is depending on the how you are depositing it, which method that we are using, and structure is changing, morphology is changing, so everything is going to change it. So features like grain size, shape, orientation and others are determined to a large extent at the early stage of the nucleation and growth and can be influenced by the deposition condition. So that is very important one. We have to optimize the deposition conditions, because without optimizing it one cannot have the film of the required desired applications. So thus detailed knowledge of such correlations are helpful for optimizing thin films production processes with regard to the practical applications. So one can see here that what are the properties of the thin films. So they are having again high surface to volume ratio. So high surface to volume ratio, so giving there that is nanoscale, and geometrical control that one can have, and it is compact one, single crystal like properties that one can have with the help of the thin film. What are the special properties of the thin films? So different from the bulk materials, because always that we have to compare with the bulk one. So what is happening here, that thin film may not fully dense one and different defects structures from bulk, quasi two-dimensional, is strongly influenced by surface and interfaces effect. So this will change the electric, magnetic, optical, thermal and mechanical properties. So one can see that if you are going from the bulk material to the thin level, that is making the thin film, then all the properties are going to change. So what are the advantages of this thin film? That is simple fabrication, high reliability, no infrastructure needed to support cell, superior performance, non-breakable, and reduction in size and weight. So one can see that these are the advantages. And now come to this non-renewable and renewable energies. So a lot of things that has been told about this non-renewable energy sources. So one can summarize it just by saying that all these that is going to collapse with the time. So one should think of renewable energy sources, and once it has been produced, then we have to store an energy storage devices that is of three kinds, that is batteries and capacitors. And there is a very interesting one that is called a supercapacitor. So we will discuss it here. So before going to the supercapacitor, try to see that what is the capacitor. So capacitor, that is it is a passive device having a two-terminal electrical component used to store the electric charge. And this is the capacitor. So two surfaces are here, that is the first one, and that is the this lower one, that the dielectric, and then the second surface, because there should be some separator here, separator is needed. So capacity that one can calculate of a capacitor by epsilon A upon D, where A is the surface area, D is the distance between the two parallel plate electrodes, and the dielectric material having epsilon here, this dielectric material that has been used as epsilon. So if you want to increase the capacity of the capacitor, then what we have to do? So first thing that we can increase this, we can choose a material dielectric constant, a material whose dielectric constant is a higher one. We can increase the surface area, we can decrease the distance, but there is a limitation. One cannot decrease this D so much, because these two plates, they are going to touch each other. So there is a limitation here. So now, if you compare the properties of the capacitors, supercapacitor and batteries, then one can see that energy storage of the batteries, that is going to be very high, and this is very high. And energy storage, one can see this energy density. Please come here, that is energy density. So energy density that is going to capacitor, you can see that energy density, it is very low one. In the battery, that is energy density, it is going to be very high. But power density, if you compare here, then power density in capacitor, that is going to be very high here. It is very high in case of the supercapacitor, and it is low in case of the battery. So one can see that this energy density of the batteries, that is higher, but the power density is low. Power density of the supercapacitor is higher, but here this uh, batteries, that is having the low one. So one can have, that's why it is better to have a system which is having both the higher energy density and power density. So this has given the birth of the supercapacitor. So if you go to the history of the supercapacitor, then in 1950s, General Electrical Engineer started experimenting components using porous carbon electrodes for fuel cells and rechargeable batteries. In 1957, H. Baker developed a low voltage electrolytic capacitor with porous carbon electrodes. That capacitor came to known as the supercapacitor, as it stored very high amount of the energy. So since it is storing a very high amount of the energy, so they have given the name as the supercapacitor. Since it is very thin one, so sometimes it is also called the ultra capacitor. So basic design of the supercapacitor, that is electric double layer. So one can see that there are the two layers that has been formed, and here porous carbon electrode, already that has been explained, so I should skip it. And this is the processes that is happening in the electric double layer. So now come to this supercapacitor, the basic idea, that is of two types, that one can have the showing the Faradic behavior, and another was the non-Faradic behavior. The Faradic behavior, there are two types, that is pseudo-capacitive behavior and battery type behavior. And non-Faradic, one can see here that electric double layer capacitor EDLC there. So examples are here, that is activated carbon, graphene, carbon tubes, and so on. So this is the EDLC that one can see here, that is electric double layer capacitor is here. So electrolyte is there, solvent is there, and it is going. So two layers are being formed. So many times that it has been explained in this lecture series. So our material, that whatsoever that we have developed, it is going to be the battery type, showing the battery type behavior. So that is the go in this Faradic behavior, so conducting polymers, metal oxides, and hydroxides, and then the pseudo-capacitive behavior and the battery type behavior, and if you combine these two, so it is going to this pseudo-capacitive battery type behavior. So this is the schematic diagram of the battery type behavior that one can see here, that electrons, they are giving this, getting this space going here, intercalation is taking place. So supercapacitor, that one can see that power density, one can here the power density of this person, that is going to be very high, that is taking part in a short distance race. Here the energy density for the marathon, that is needed high, so the energy density of this person is high. In India, that is in different parts that we are doing the researches, but unfortunate part is here that we are unable to collaborate with industry. So industry is not coming forward, and there is certain reason, because that I will explain later on. So let us see here that in China, there is a prototype Shanghai supercapacitor electric bus at recharging station, and cost one can see here, and its speed limit is 45 kilometer per hour. Capacity is there, distance that it can travel from 5 to 9 kilometer. Charging time is 5 to 10 minutes. So this can be used as a city bus there. They have advanced, they are developed the advanced version also. So supercapacitor for the solar power station, that one can have, from the solar power one can take the supercapacitor bank, then we can charge here this battery bank, and then you can use here the household and other things. So what are the advantages of this one? That a high energy storage, wide working temperature. That is very important one, because if you go to the different parts of the world, then temperature it is varying very high one. So it is working from minus 40 degree to 60 degree centigrade, eco-friendly, quick charging time, maximum life cycle, high cycle efficiency, high specific power up to 17 kilowatt per kg, extremely low internal resistance, and moreover it is going to be the safe one. So maximum cycle means that we can charge it for many number of the cycles, charge and discharge one. And after charging and discharging, one can see that there is a high cycle efficiency that is going to be 95%. So what are the disadvantages that one can see? The disadvantage of the supercapacitor are here, that low energy density usually holds 1/5 to 1/10 of a battery. The voltage varies with the energy stored. So as the energy that is going to change, here voltage is also going to change. Have high self-discharge rate. So that is also a big problem in case of the supercapacitor. So these are the some drawbacks or disadvantages. Now come to the thin film again, because my work it is related with the thin film. So there are the different ways that one can develop the thin film. Just wait for a moment. Well, that is basically we can divide the thin film deposition technique into two parts. That is physical method. We also call the top down approach, and the chemical method, that is bottom up approach. And in this physical method, one can see that vacuum evaporation method is there, and there are having this type, the resistive heating, flash evaporation, electron beam evaporation, and so on. Sputtering, that if you are coming, then glow discharge, that is this is sputtering, triode sputtering, and so on, that is there the sputtering one. And if you are coming to bottom up approach, then there are the two categories here, that is gas phase and liquid phase. So in gas phase, one can see that there is a chemical vapor deposition, laser chemical vapor deposition, photochemical vapor deposition, and so on. In the liquid phase, that we are having the electrode deposition, chemical bath deposition, successive ionic layer absorption and reaction. So we call that the Silar method, and some other methods are also here. So basically that in our research that we have used this Silar method. There is a reason for that one, I shall discuss later on. So what is the Silar? That is successive ionic layer absorption. It is not the absorption, but it is the absorption. Here it should be D. Sorry. Here should be D1, absorption and reaction. So we take the 4 beakers here, and the substrate is, we dip this substrate here, then dip in the double distilled water here, to remove the loosely reacted ions, and then the anionic and cationic solution alternate and DD water. So just a symbolic one I will explain later on. And here that is layers are formed one, and in this way that we have deposited this thin layer on the substrate. I shall discuss later on. Let us see it here. So these are the some basic requirements. Now come to the experimental one, the second part of my lecture. So second part, that is here. So we have started the work on the strontium hydroxide, because it has not been reported earlier. So we thought that we should start from the strontium hydroxide, and the Capacitor basically has done this research. So come to this Silar method. What is there? So we have taken the strontium nitrate, and here this Di water and Di water here, and sodium hydroxide. Basically that we have started this work having no experimental facility. And it is very interesting to know that we are having these 4 beakers. With the help of these 4 beakers and the chemicals, and with the help of this substrate that we tried, that let us see that whether we are able to deposit this thin film or not. So in this process that we have done it, and one can see that the substrate, it is being deposited in the sodium nitrate, then some of the ions that is going to deposited here. So it is the strontium ion that has been deposited on the substrate. Then some of them that will be loosely bound. Then what we do, we put in the DI water. So if you are dipping in the DI water, then loosely bound ions or unreacted ions that is going to be dissolved here, that is going to in DI water. Then here that we have taken the sodium hydroxide, that is OH ion reaction that will take place here, that is then it is going to form the sodium hydroxide, but after sodium hydroxide, but after that chances may be that some of them they are loosely bound, so we have to put here in the DI water again. So if you are putting in the DI water, then loosely bound species they will come out, and this is called the one cycle. So we have to repeat it. So here that is one can see that we have to optimize it. Optimization is also very necessary one. So how much time that you have to dip in this first one, and the second one, how much time that you have to put in the DI water. So we have optimized it, and optimization that shows here, that is, let us go back. Oh, sorry, I am going in forward direction. So see that we have optimized it, that is it should be here in the for the 20 second, and then it should go to the DI water for the 10 second, then to the sodium hydroxide here, that is for the again 20 second, and to DI water that is going to be 10 second. So in this way, that is the one cycle that has been completed. So we repeated it for the 20 number of the cycles. So one can see here that is schematic diagram of the deposition of this thin film, that is substrate is here. So strontium ion that is being absorbed, then it is reacting with this OH ion. So strontium hydroxide that has been formed. So manually that we have done it, and after the sample that has been prepared, then we have to characterize it, that whatsoever the sample that we try to make, whether it has been formed or not. So for that, we go for the XRD. So one can see here, that is the XRD pattern of the strontium hydroxide thin film on the stainless steel substrate. So this is for the stainless steel. So one can see that pics are here for the stainless steel, and here that we are having this 011 phase and 400 and 411 013. So one can get the information that which type of the material that we have developed. Further that we have seen that here this FTIR spectra of the strontium hydroxide. So different bonds that were being formed here that has been represented, and this is known as the fingerprint region. So in the fingerprint region we are having this one, and this is the due to this OH that is taking place. Now come to the next one. So this proves that strontium that has been here, different oxides and others bonds that is present here. So probably that I can give you the exact data. So at 439, one can see here that at 439, that one peak that we are getting here, this is due to the oxygen, strontium oxygen bond, and this 4981, no, sorry, 98 inverse, it is giving this hydrogen strontium OH, HSROH1, and in addition to that one, we are having the 1439, that is the vibration of the water molecule here, that is HOH, and the peak located at the range of the 3300 to 3800, this is going to be the stretching vibration of the physically absorbed the peak of the OH, because we are doing here this in atmosphere, so that has been OH that has been absorbed there. Why we have chosen the strontium hydroxide? Because we are not having the sophisticated laboratory. So in the air medium that we are doing here, so whatsoever the material we are choosing, it may be going to be, if you reacting to this air, then that will be oxidized. So that's why already that we have taken this sodium hydroxide. So there is no effect there. So if you see this FESM structure, then they're very beautiful, that tuberose structure is here. So if you see it carefully, then one can see that this tube, due to this tuberose structure, what is happening, that surface area is going to increase. Here the surface area that is going to increase, and one can see here the inset, that is so the EDX. In the EDX that we are having the different components here, that is strontium is present here, oxygen is present here, and there will be some peak due to the carbon. So if you are doing in the open air the experiment, then the carbon peak that is also present there. So this is the magnified form of the FESM. So FESM is here. This magnification, it is going to be the 1 micrometer. So if you are going to this magnification of the 1 micrometer, then one can see that very beautiful tuberose structures that we are having. This is at 200 nanometer, and here that is the same one that has been magnified. So one can see that there are the different pores here, and the branches that has been developed. So due to this one, a specific heat, that a specific capacity is going to increase. So this is the TEM image of the strontium hydroxide, and this is the TEM image. So again, that one can have the tuberose structure, and this is the HR TEM that one can see, and inset is the electron diffraction pattern of this, and this is the EDS pattern, and EDS pattern of this D of the strontium hydroxide scratch powder. So see that scratch powder that we have taken and then sent for the stem characterization, and we are doing it manually. Really, the students, they have done very hard work, because manually that we are doing, completing one cycle, then two cycles, then three cycles, and so on. So if you are completing for a large number of cycles, then a very few amount of the strontium hydroxide is going to attach on the substrate. Then we have to take it out, and we have to do it again and again, so that a required amount, that is some very small amount is needed, but it has taken a long time to deposit it manually. So the student, they have really worked hard here. So as I was talking about the carbon, one can see here that carbon that is present here, and this is the strontium, that is strong peak is there, oxygen is there, and other things are also related. So come to the application side. So once we have made this thin film of the strontium hydroxide, we have characterized it, and we have obtained that okay, it is the strontium hydroxide that has been deposited. Then what will you do? So our aim was to have this supercapacitor, to see the application as a supercapacitor. So for having this application as a supercapacitor, then we have to optimize the number of the cycles. Then first of all, that we have taken this CV that we are cyclic voltammetry curves for the 10 cycle. So for 10 cycle, one can see that is the rate 1. So covered area, that is going to be very small one. And when we go for the 20 cycles, then one can see that covered area that has increased. But we are of the favor that if you go to the 30 cycle, then again it will increase, but one can see that it is not increasing, but it is decreasing. So what is happening there? Why it is decreasing? Why it is decreasing? Because one can get answer from here. So many tube rows that has been developed. So what will happen? These tube rows that is going to cover the surface area. Surface area is going to reduce. So that's why one can see. So one has to optimize the number of the cycles. So number of the cycles that we have optimized, then one should use that what the electrolyte that we have to take. So we have to optimize for the electrolyte. So here we have tried for the lithium chloride, then KCl, then Na2SO4, then NOH. So for the different electrolyte that we have optimized it, then one can see that after optimize that we have fixed the cycle, then we have chosen the appropriate the electrolyte. Then we have to see that this is the CV curve at a different scan rate at 1 mole NOH electrolyte. So here one can see that for the electrolyte I have not uh, discussed it, but one can see for the NOH, the CV curve, this is for the NOH, so it has having this largest one. So we optimize it here, and then for the different scan rates. So scan rates, it is your 5 millivolt per second to the 200 millivolt per second that we have put there. And then we have seen that as we are increasing the scan rate, the specific capacity is decreasing. So it is having the maximum value at 5 millivolt per second. So at this one, we are having this maximum one. So maximum specific capacity achieved, it is 308 coulomb per gram at 5 millivolt per second scan rate. So after the CV, there is another way also that one can have this, we can study this specific capacity, that is charge discharge here, galvanic charge discharge method. So here that we have done for the charge discharge one, for the various current density. So current density that we have taken this 1 milliampere, 1.5, 1.2, and we have seen here that which is going to give you the best result. Then B part, that variation of the capacity retention of the strontium hydroxide thin film electrode with number of cycles here. That number of cycles that we have tested it up to the 5,000 cycles, and one can see that it is coming lowering down. It is up to the this limit, that is up to 500 or 600 or so. It is going to 50 degree, and but from 50 to one can see this lowest one. It is about the 39 or so, or nearly 41. So it is coming after this 5,000 charge stars one. So that is also very necessary one. Then one can go for the Nyquist plot. So in the Nyquist plot also, this is the experimental strontium hydroxide, then fitted curve here, and the equivalent circuit that has been represented by this equivalent circuit. So this RS RCT that has been obtained, 3 resistance one on 1.52, for a better this super capacitor, this RS value that should be small one. So let us summarize that what we have done, that is the strontium hydroxide tuberose structure that we have obtained with the help of this CELAR method, and the structural study that is confirming the orthorhombic nature, and it is having this value that 413 coulomb per gram at 2 mA current rate in 1 molar NOH electrolyte. See here that we have to fix the electrolyte here, number of the cycles and so on. So obtained value, it is going to be 413. It is an encouraging result in the sense that this is going to be the first report on the strontium hydroxide. Then it is our responsibility that how we increase the specific capacity of this material. So we thought that let us dope some other material. So we have done the doping. So different dopings that has been done, that is iron, copper, yttrium, and so on. So here I would like to present that is the doping effect of the doping, that is yttrium doping in the strontium hydroxide. So we published in this energy journal. So the same method that has been used here, that is strontium nitrate and YNO3 into 6H2O, that has been taken here because we are making the doping. So a fixed amount that we have to take it, and we have to mix with strontium nitrate so that one can get it this proper doping. So then for the 20 cycles again, that we have optimized the number of the cycles, so it has come to the 21. So after 20 cycle, that this thin film that has been formed, and one can see that this is the structure here. This is same image. Yeah. After that, having this synthesized, we have synthesized it, and then we are coming to this XRD pattern. So XRD pattern that one can see for the YSR, that is 1% atomic percent, 2 atomic percent, 3 atomic percent, 4 atomic percent doping. So we are getting here that is the same peak, same type of the peak also. Slightly it is changing the nature due to this doping one, and the FTIR analysis also, that one can have the same type of the structure. Slightly it is changed due to the doping one. And come to this FESIM. In the FESIM, that one can see that what is happening here. That is in the previous case, in the case of the tube, this is pure strontium hydroxide, we are having the tube rose structure. But it is very interesting to see that in three-dimensional, three dimension, it is popping up something more, that is popping up due to the doping of the yttrium. So this due to doping of the yttrium, one can see that it is pop up in this form, and in this way it is increasing, further increasing the surface area. So as the surface area is being increased, that one can see that how the yttrium is affecting its same image. So same image, that tube rose, and along with that one in three-dimensional it is coming up. So in this way it is increasing the surface area. So the characterization that one can have the EDX. So in the EDX also, that yttrium is there, strontium is there, oxygen is there. So this so confirms that the doping that has taken place, and one can see that weight percentage of the different component that is given here. Strontium 63.5, and oxygen, it is your yttrium is here. And these pictures also present you that whatever the doping we have done, it is there. Strontium is also there. So it has confirmed. So it has confirmed, then one should go for the CV. So CV, that one can see that CV that we are having, this is a CV curve for the 1 atomic percent, 2 atomic percent, 3 atomic percent, 4 atomic percent, and this is going to increase your specific capacity. So specific capacity is being increased. Then one can go for the charge discharge, the galvanostatic charge discharge curve for the undoped, and the 1, 2, 3 atomic doped of the uh, strontium hydroxide. So one is having, this is the galvanic charge discharge, and due to this one, what we obtained, that its specific capacity is going to increase, and then one can see the capacity retention. So capacity retention, that is also going to increase it here. So basically it is going to be maximum after the 1000 cycle, it is going around this 70% or so. So capacity retention that has increased, and the highest value of the specific capacity, in the previous case it was the 400 something, and it is going to increase to 705. So specific capacity that has also been increased. So this has been given the improvement there, and the Nyquist plot that we are having, and the corresponding this uh, diagrams are there, Nyquist plot, and Bode plot, that C is having this Bode plot here, and so on. So let us see what is the information that we are getting. The cyclic voltammetric, galvanostatic charge discharge, and electrochemical impedance spectroscopy measurement show the supercapacitive battery-like response. So after having developing this, increasing the specific capacity, and this cycle stability, that we move forward to make the device. So we cut this one in two L-shaped type, and then join it together to form this device. So this is the actual photograph of the fabricated symmetric solid state supercapacitor YSR electrode. What is the symmetric? because both the electrodes that is made of the same type. So whatever that we have fabricated this device, we have to see this electrochemical performance. So this is showing the electrochemical performance, and one can see that potential, that is very important one. Potential, it is coming from 0.0 to 1.6. So potential window, it is going to be 1.6 here. So that is very important one. And here potential window is also 0.0 to 1.6. So this YSR fabrication, it is showing that potential window here. And this B, it is saying CV curve at different scan rates. So if we are changing the different scan rates and try to see that what is going on, how the change is taking place. So we have calculated this specific capacity. After that, the energy density and power density has also been calculated. But this is very interesting to see that the potential window is from the 0 to 1.6. So 1.6 is going to be the potential window. So this is the charge discharge that one can see, that charge discharge of this YSR fabricated. And then the galvanic charge discharge of the device at various current rates, that 0.1 milliampere to 1.2 milliampere current rate, and it is having the highest value for this one, that 0.1 milliampere. Then this is the actual photograph, which is showing the photograph of charging of the two devices connected in series using battery. So first of all, we have charged it with the help of a battery for the 3 seconds. Then what we do, that is come to the second one, photograph charging of two series connected by this red LED. So we have connected this red LED. Then E part, that is a schematic diagram of the discharging of this one electrode. So one can see that charging that one can have, then charging that we are doing it here, sorry. So we have connected it, and then we are charging it here. So charging that is taking place here. Then the discharge here with the red LED. So we have attached the red LED, and one can see the photograph after the 3 seconds, after 17 seconds, after 31 seconds, after 50 seconds, after 60 seconds, and after 70 seconds. Even after 90 seconds, that one can see here that LED is glowing. So that is a very interesting result, that we made a device, and this device is the working one. Further, that is cycle retention also that we have calculated, and cycle retention for the up to 1000 cycles that one can have. So here that is up to 1000 cycles that we have made, and it is coming about this 60%. Then this B is the Rogan plot here, and here that you will see that it is the fuses here, and conventional capacitors are here, and lithium ion batteries that is here, that is specific power and a specific energy. So we call this Rogan plot here. In my case, that we will observe that as fabricated YSR is here, so here that is a specific energy, a specific power, it is decreasing as a specific energy is increasing. So this type of the behavior that we are having. And Nyquist plot that we are having, the experimental and fitted data, and these are some other characterization. So interesting thing is here that we are supercapacitor, that whatever the device that we have made, it is lying here. So we have obtained, let us summarize it, that is YSR by SILAR method, and the high stability of 1 atomic percent YSR, that is 85%, and prototype device, that is symmetric supercapacitor, both electrodes are same, has been assembled, and the specific capacitance obtained from the fabricated device, that is 31.8 farad per gram. Moreover, the highest specific energy, it is 6.64 watt per kg, for the specific power of this one, that is 271 watt per kg here. So let us move further. So further that we have been obtained this that a specific capacity, it is increasing So by doping in the strontium hydroxide, then we tried that let us form the composite. Is it possible to form the composite? So we tried in that direction and we were able to synthesize the aluminum hydroxide and FeOH composite. So this composite that we have made here, and it is the modified form of the Silar method, or this is called the layer by layer method. Layer by layer method means first of all we make the layer of the aluminum hydroxide and then another layer of the iron hydroxide, say FeOH after that one. Then this will call that is the one cycle. And really all the things that you will be surprised to note that we have done it manually. So manually that we have done, we have taken from the first one that substrate, and probably that I have not explained, but it is very interesting topic that how we can clean the substrate, because uh, a very clean substrate is needed. Otherwise, if suppose that already something is deposited, then one cannot clean it. There is a fixed procedure. So one should use that fixed procedure to clean the substrate. So this is the first one that one can have. This is the dipping in the having this aluminum ion there, then rinsing it with DI water, then NOAH reacting with this NOAH. Then what will happen? That aluminum hydroxide that will be formed. Then rinsing with this DI water. So layer of the aluminum hydroxide that has been formed with the help of these four beakers. Then we have dipped to have this absorption of this iron, then again rinsing, then this reaction with the ammonia solution to have this FeOH. So in this way, that is going to complete the one cycle. So this is a one cycle. So we have to optimize the number of the cycles, and then we have to choose the appropriate electrolyte and so on. So here one can see that HR same image of the A part. One can see that FeOH is here, and B part, that is B here, that is AFO, and this we call this one as AFO because short form, that is aluminum is here and iron is here. So we combined it and we called given this name. This is the bigger one, so we have given the name as AFO. So this is the AFO. One can see the HR same image. So from here to here, if you see that it is quite different one, and we observe that surface that has been increased here with the help of the same images. And then C part, it is going to for the FUS and AFO that has been compared, and one can see that C and D. So FUS that is here, and it is elemental analysis that one can see, and AFO that is here, one can see that F to G that is here, F to G that we are having HRTM images of AFO. So in case of this AFO, one can see that we are having very beautiful same images, and which is quite different from the FUH or the this aluminum oxide. So basically, just by seeing it, one can observe that its surface area is going to increase, and elemental analysis that shows that all the elements that is present here. The same thing that we have done here, that is cyclic biotmetry of the assembled symmetric device at potential window 1.00, 1.20, 1.30, 1.40, and 1.45 volt at 1000 millivolt per second. So for that one that we have done here, this CV, and then B part CV curve, that once we have optimized it, then one can have this CV curve at different scan rates. So this is the for the different scan rates that we are having, and further that one can go, that is galvanic charge discharge curve. So charge discharge curve, that the same type of the things that we have to do, and for the different current rates we are having the charge discharge, it is having this highest value at 0.1 milliampere. Then D part one can see that is Rogan plot here. So Rogan plot that one can see that present work that is here. It is here. That is energy density that is going to be very high one, and the power density and energy density relation that is given here. So come to this E part, that is capacitance retention. So that is the very important one. So retention that one can see that after 1000 cycle, uh, here up to the this one up to 800 cycle one can see that is a retention is very good one. After that it is decreasing one, but it is decreasing up to the 70% or so. What is important here, that again uh, we made here the device, because making device is very important one, and you can see the show the practical applications. So we have taken here the symmetric device, and symmetric device at different times that one can see that with the help of this mobile one can see the photograph here. This mobile is there. So with the help of this mobile we have switched it on and then make the photograph. So just after the 1 second, here this is the 1 second, it is glowing. After 15 seconds also that one can see that it is glowing here. This is a red color LED is there, so it is glowing here. Then after 30 seconds also that it is glowing. After 60 seconds also that we are having this red light, it is glowing here. And after 108 seconds also that is glowing. So in this way that we can say that this fabricated device, it is of industrial use that one can use it, and very good value that we have obtained. Probably that I have given its value. Let us see it in the conclusion part. So if you summarize here, then we employed this binder free or whatsoever that chemical that we have, it is binder free one, and layer by layer method, that is modified form of the Silar method. So one layer of the one material, then another layer of this another material. So first of all that we have deposited this ALOS thrice, and after that we have deposited this FeOH. So that's why it is layer by layer. That's why it is called layer by layer method. And one can see the result here, that electrochemical analysis of this aluminum hydroxide FeOH electrode shows high specific capacity. So that is very important one. In the previous two cases that we have seen the specific capacity, that was in first case it was around 500. In the wide doped strontium hydroxide, it has gone to this 750 or so. But here one can see that is a specific capacity that has increased this amount, that 2576 coulomb per gram at a scan rate of 5 millivolt per second in this electrolyte, that we have to optimize whatever that we have done in the first case. In this case also, that we have to optimize the number of cycles, then we have to optimize this electrolytes. So which electrolyte that we have to choose, then at what scan rate that we have to we are obtaining the maximum value. So this is the result that we are having, as well as it has a low solution resistance. Solution resistance is very low one, so 1.335 ohm. So that's why this is very much suitable for the application side, and good cycle stability. So one can see that cycle stability that is coming 72% of its initial value after the 1000 cycle. So if you are using it up to 1000 cycle, then its stability it is decreasing only to 72. But this number that if you see the specific capacity, that is going to be the very high one. And after getting this very high value, so we made a prototype flexible solid state symmetric pseudo capacitor device. And we have taken this PBA and 1 molar Na2SO4 gel. So this gel that we have made it because to separate these two electrodes, the highest specific capacitance was obtained as 225 here farad per gram at this current rate. And potential window also, that is going to be very good one, that is 1.45. so potential window is also very good one. So this can have the industrial application because its specific capacity is also good one. So one can see that energy and power density of this assembled device that has been calculated. So energy density is this one, and power density that is going like this one, that has been obtained. So this is a very important result. So thus the result signifies that porous coral leaf, here we are getting this coral leaf sponge-like structure of this material, that ALOS thrice FUS composite material can serve as a promising electrode for flexible portable energy storage device for supercapacitor applications. So now come to the third part of my lecture here, that is a presentation, that is what is fractal. As we have seen that Professor Lakshman has already covered, and we got this idea that how this theoretical idea that can be uh, applied here and get some more information. So in India, that is theoretical and experimental side both, that is open, and we should try to do the theoretical work also. And from the theory, whatever the information we are getting, we can give this input to the experimentalist so that they can use it and they can make a better device. So what is this factor? Fractal, basically it was this term that has been used in mathematics. So an object or a mathematical set with a self-similar pattern is called factor. Self-similar, that is, it's one can see that if you take a very small portion, then if you grow it from that, then you can develop this whole space. So same case is here. Take the smallest one, and then from that smallest portion, you can grow the whole geometry. So fractal is a geometric pattern that repeats itself at smaller and smaller scales to produce irregular shapes and surfaces that cannot be represented by classical geometry. So whatever the geometry, classical geometry, if you use, one cannot represent it. And see, that is best example here, that two examples are here, cauliflower and this one. So fractal study, if you see, so in this that we have shown this fractal one. So fractal characterization analysis, that parameter, there are two parameters. See that if suppose that this type of the shape that we are having, if suppose that this is the shape, irregular shape that we are having, and whatever the tip, if you are using this type of the tip, then this tip will not cover this whole geometry, and this tip that will show that it is having this type of the geometry. Similarly, if this gap it is more and very narrow tip that we have used, then it is giving this some they are different one. So one has to have the very appropriate this material, the appropriate object to study it. So one can see that parameter, that is interface width and average roughness, are going to be this global characterization of the roughness, but it is missing out the surface profile. Although that we can measure the interface width and we can measure the roughness, but the surface profile, that is, it is missing here the surface profile. That what is the surface profile, exact surface profile? Roughness measurements are depend on the scale resolution. That here one can see that resolution, that is scale of resolution, that two scales that we are having, then we are having the different result. The interface with W and average roughness, that is RA, are only sensitive to the peak values of the surface profile. So what is the peak value that one can see here? That it is sensitive to that one. But these parameters do not give information about irregularities. So they are not going to give you more information about the complexity of the surface. So fractal analysis can provide richer characterization of the surface morphology and deeper insight into the surface creation processes. It is a scale independent property. So that is also going to be very important one to state here, that it is the scale independent property. So we have used this copper doped strontium hydroxide and we have made the fractal characterization. So the Higuchi algorithm that we have used, and already Professor Lakshmanan has given deeper idea about this one. So with the help of this depositions, one can see that one can calculate this fractal dimension here and the Hertz exponent. So Hertz exponent and fractal dimension. So we have applied this one and obtained this type of the result. So how one can say that it is having the fractal nature? So it is very easy to obtain this result, that see that if you plot a graph between log k and log lk, and if you are getting here the straight line, it means that it is having the fractal nature. So mathematically very easy to obtain that whether it is having fractal nature or not. So for that one you have to plot this curve, this log k and log lk, capital Lk. So that has been defined. Professor Lakshman has very well explained what is this Lk, what is your k. So sir, so one can see that it is becoming a straight line, though showing that is fractal nature. And then this is the fractal nature one can see for the 1 atomic percent doped copper strontium hydroxide, 2 atomic percent, 3 atomic percent. And for that one, number of the pixels and the fractal dimension that has been calculated. And here the number of pixels and the Hertz exponent that has been calculated. So we can see that these samples, that 1 atomic percent doped copper strontium hydroxide, 2 atomic percent doped, 3 atomic percent doped copper strontium hydroxide, the fractal, that is dimension, that is calculated like this one, Hertz exponent like this. So whether it is corresponding to the obtained result or not, this is the theoretical one. So one can see that it is having the maximum value for the 3 atomic percent. So let us check it here. So one can see that is the charge discharge and comparison of the specific capacity with various current rates, just for the experimental side, the same repetition. And one can see here that fractal dimension, Hertz exponent, and the specific capacity if you calculate. If you compare, then the 3 atomic percent copper doped strontium hydroxide, it is having the fractal dimension, that is the highest value, and the specific capacity is also highest one here among all the three. So it means that whatsoever the theoretical that result that we are getting, it is supporting the experimental result or vice versa. So one can see that a specific capacity, it is showing that this particular, the third one, it is more rougher one. The surface area is increasing. So if surface area is increasing, then the specific capacity is also increasing. So we have applied this another curve for this iron doped strontium hydroxide. Here also that we are getting the straight line, it means that it is showing the fractal characteristic. And then we have calculated the specific capacity, and one can see that fractal dimension of this Fs2, that 2 atomic percent doped iron iron doped strontium hydroxide, it is having this fractal dimension 6.789, this one, and one can see that the highest fractal dimension and corresponding to the highest value of the specific capacity. So this is also supporting this experimental result. So one can conclude here that SEM reveals the surface morphology qualitatively, and the quantitative surface analysis has been done using the classical technique as well as the fractal analysis. The relationship between the fractal and supercapacitive behavior of the electrode has been explored. The fractal analysis shows that the fractal dimension increases due to the copper and iron doping, which is consistent with the experimental result. So therefore, we conclude that fractal analysis provides important information about the supercapacitor electrode. And here I would like to mention that very first time that our group has used this fractal concept in the supercapacitor. So this is my small group. Kabisri has completed her PhD degree, and the Sama Praveen, Sunil Kumar. Sama has also submitted the thesis, and his viva that will be probably on the next week. After that, she will get the degree. So Sunil Kumar Singh, Priyanka Maurya, and who is this fellow? That is his name that I have written it, but Abhishek Kumar Sahu.
Abhishek.
Yeah, that I know very well. My group members, Abhishek Kumar Sahu.
Yes, sir.
Yeah, I know it. I know you very well, but I wanted to show that whether I have written it, but it is not coming. So Abhishek Kumar Sahu. So I thank these people that they have given the chance to learn about this supercapacitor, and without these students, I am not able to understand that what is going on the experimental side. And really, they have done very hard work, I can say, because manually that you are doing the dipping here for 20 seconds, then to the another one for 10 seconds, then another for the third beaker for the 20 seconds, for the fourth beaker again going to the 20 seconds. So manually that you have to repeat it, and then layer by layer if you are going, then we are having the 8 number of the beakers, and in these 8 beakers that you have to do it by 20 cycle, 30 cycle, or 4 or so on. So but it is also important to see that for TEM characterization, that some particular amount of the deposited material they want in powder form. So we have to deposit that many days that they have taken to deposit it, they scratched it and then send for the TEM characterization. Sometimes that we send it, they are saying that your amount, that is whatsoever you have sent, it is not sufficient one. So please make some more, send some more amount. So we have to repeat it. But that is manual one, and with the limited facility that we have developed all these electrodes, and we try to make the device. So one thing more that I should discuss, because it has not been considered. So let us see here. Yeah, this one. So in literature, please make it clear, otherwise it is giving trouble all the time, that if you go through the literature, then sometimes they are reporting the result in terms of, they call it as a specific capacitance, and they are giving the result in farad per gram, a specific capacitance and result. Oh, where it is? So a specific capacitance, somewhere it is written and it is farad per gram, somewhere it is given the specific capacity coulomb per gram. So there is a confusion that when we should use the term the specific capacity, when we should use this term the specific capacitance. So that depends that which type of the CV curve that if you are having. If you are having this type of the CV curve, then certainly that we have to use this formula, and we have to see that it is a specific capacitance. If you are getting this type of the CV curve, then in that case we have to use this formula, and here we have to call this one as a specific capacity. Conway in his paper, probably it is not written here, he very well explained that when we should call this one as a specific capacity, when it is the specific capacitance. And if you are saying the specific capacity, then it is going to be different unit, capacitance that is going to be different unit, and the formula is also changing one. So depending on the CV curve, that one should use this terminology. thank you for your patience listening. So I should skip because I cannot open this video. Now I should open this video.